Well, hello, everybody. I don't want to take up too much time, but I'd like to introduce our panel. We have Kate Cooper from University of Nebraska Omaha, Chris Brooks from the University of Michigan, Rayed Ghani from the University of Chicago, and David Goodsmith from datascience.com. Each of our panelists is going to come up and give a brief talk, maybe 5-10 minutes. And in case you haven't looked up what this is about, the panel is going to focus on reproducibility and gold standards across domains. I'm sure probably many of you have read some of the recent articles on how a lot of medical research is not reproducible. So a lot of publications are coming out, and then when you look, when people actually try and recreate what those researchers did, they can't reproduce the results. So we're generating new scientific research or results quicker than we can validate and verify them, which is a pretty big problem. Even in computer science, machine learning, a lot of the conferences I go to, I'll read a paper and say, oh, this is a great idea, but then I look and maybe I'll find the code, but then I can't find the data that they worked on. It's a pretty challenging problem. We have all these research papers being generated, but we're not necessarily checking to see to validate our results. So like I said, I'm going to keep it quick, and Kate Cooper is going to come up first.
Hi, thank you. So I'll try to keep an eye on my time here. Again, my name is Kate Cooper. I'm an assistant professor at the University of Nebraska at Omaha. I work in the School of Interdisciplinary Informatics, and as a part of that, one of the things that we do is bioinformatics, which is what I'm a classically trained bioinformatician, one of the first from the university, actually. I'm kind of in the area of bioinformatics and biomedical informatics, and I've tried to identify a number of issues that were just mentioned that we run into in biomedical research on the topic of reproducibility. I've actually come up with an acronym that I affectionately refer to as GER that addresses these concepts. The first being generalizability, and then the 5 R's that follow that you could argue some may be the same, some may be different. Reproducibility, replicability, robustness, rigor, and reliability. And all these things are aspects that have not been adequately addressed in biomedical research. Some of the issues that we run into are a black box type of approach. We have a lot of tools in bioinformatics, in biomedical research that are available open source, and we've been a big part of the open source initiative trying to make code available under Creative Commons licenses, that sort of thing. But the problem is people just take a tool off the shelf and apply it to their data without knowledge of the algorithm behind it. One of the most famous algorithms that we have in bioinformatics is called BLAST. It's been available since 1990, and even some bioinformaticians don't truly understand what are the implications of that algorithm. So garbage in, garbage out is the first big problem. Second problem is experimental reproducibility, as was just mentioned. A recent study examined the same data set, looking at Zika virus, tried to apply the same methodology, came up with 3 different results, which should not be happening. In our research publications, we should be able to delineate what steps we're taking in a way that it can be reproducible on the same data set and also on new data sets with consistent results. We also have peer review is becoming something of a problem. We have a failure to publish negative results. We have bias towards publishing of positive results. I think that's applicable across all domains. We have, of course, common problems, data storage management, data siloing of health information. HIPAA regulations make that more difficult as well. And then also we have a massive generation of data and a failure of development of methods to extract knowledgeable information, which again I think is broadly applicable. And then finally we have integration of behavioral, environmental, and genomic data sets. As you can imagine, you have your medical history that you go to the doctor and you say, oh, I'm sick, I need a certain drug, or I need some treatment, or I need some plan to help me survive this illness. The problem is that we don't have methods to integrate what does your genome look like, what does your proteome look like with daily behavioral data. I mean, this is too much work for the physician. It's too much work. It's just overwhelming for the field. So this is something I think is on the horizon, but we have, until we establish this concept of reproducible research, my GER acronym, we're not going to be able to do those things. There's a couple applications that you may have heard of with regards to machine learning. where it was successful. For example, a study in 2002 by Nature took 6,000 genes and were able to predict long-term survival in B-cell lymphoma patients based on just gene expression. So we do have some successes that are out there, but before we can truly move forward and make, I think, these big strides, we need to address these concepts of reproducibility, reliability, robustness, et cetera. So that's actually one of the research areas of my focus, and I'd be happy to answer questions later on the panel. Thank you.
Hi, I'm Chris Brooks. I'm a computer scientist. I'm in the School of Information, and I actually have a dual role. I'm also Director of Research and Learning Analytics at our Office of Academic Innovation. And that office does a number of things, including, but some focused on pedagogy, some focused on technology, and a lot focused on MOOCs. So I wanted to talk a little bit about my domain of interest, research-wise, which is big data in education. This is not necessarily teaching data science, although I do that as well, but it's actually applying data science to educational data. Ed data is getting big and multifaceted. There's a number of different systems on campuses that we're starting to be able to tap into that have large, everybody's going to clickstream events, for instance, like every application, and so the size of data is getting quite large. There's really two sub-communities that are interested in issues of data science as it applies to learning and education, and that's the learning analytics and knowledge community and the educational data mining community. And what are the core tasks these communities are interested in are predicting student success. And you can imagine lots of reasons why we might want to predict student success, but almost always it's to intervene and try and help other students become more successful. Some of the different kinds of data in these domains, there's these core sources of data, so student information systems, learning management systems. More and more we're using external sources of data. Some of these are official and curated, like the National Student Clearinghouse. Some are scraped, actually, like LinkedIn, to try and identify, for instance, STEM students and getting STEM careers. And then what you can't see on the bottom of the slide is that there's a bunch of other kinds of data sources are really interesting. Text data being actually the big one that's kind of right now hot in the field, trying to manipulate, understand, and link in text data with all of the other semantic data. Sharing data is extremely hard in the community. So IRB issues, FERPA issues, and institutional agreements, and really context is everything. And so an instructor changing a few things in their course dramatically changes the data, and we often don't capture that context. Recently, there's this new data source, which are these massive open online courses, such as those on Coursera, edX, FutureLearn. And this is exciting because we have tens of millions of individuals taking these. For instance, at Michigan, we have, I think, 6 million users have taken one of our MOOCs. We have something like 3 billion clickstream events just from the last year and a half alone. And so this data set is getting really exciting and has caused a new generation of researchers in the area who have a computer science background to get more involved. Predicting student success in MOOCs, though, is a little bit of a wild west. First, we're not even aligned on what's important to predict: dropout, stopout, conversion to paid, re-enrollment, etc. We also don't share data sets, confidentiality reasons. So we tend to have big numbers, millions of users, but only in 1 or 2 or 3 different courses. And so the chance that we're overtraining on those is quite high. And the most disturbing is that there's no sharing of code or details of methods, and reporting of results is poor. So I also have an acronym, and on the right you'll see there's this table, and this is common in the literature in this area, where people will try every algorithm in their toolkit. Let's say they're using Weka. They just go through all the algorithms, report on them all, and they'll report on all metrics, and they'll contextualize none of it to the particular problem that they're trying to solve. And of course, we know when you try many, many different things, you're undoubtedly going to find something good, and the chance of it being a spurious result goes up. Here's 3 examples of paper, one of my own included, that would be probably impossible to replicate, and all are trying to do generally the same thing and can't be compared to one another. So one of the things that we can do, we're starting to look at towards building architectures to support researchers running their code on data sets that are embargoed, that are held back in a sort of data enclave. And so in this, this is some work that we're doing with colleagues at Penn in Illinois, where the analysis methods are provided as a sort of Docker container. It's then distributed to all the institutions. The results are filtered back, and all the metrics are reported. And so there's a standard set of metrics, a standard set of outcome variables, and a standard data set which isn't distributed but is available to researchers.
So my name is Raed Ghani from University of Chicago. I want to sort of give a slightly different perspective because a lot of the work that we work on is really in sort of areas of public policy and kind of social impact. So most of the work is with government agencies, nonprofits, with extremely confidential and sensitive data. So examples of things we've done include working in Chicago around lead poisoning to get very sensitive data about kids and their lead tests and where they live, and using that to preemptively figure out which kids are going to be at risk of lead poisoning, and then sending lead hazard inspectors to their home to check for lead and fix the problem before they get lead poisoned, as opposed to today they do it afterwards. Or another example of work we've been doing for the last couple of years is working with police departments on helping them identify which officers are likely to use unjustified use of force, or do things that they shouldn't be doing. If we can predict that in advance and then provide that information to their supervisors, there are interventions in place. Again, there are preventative, as opposed to today, you do them after the fact, and all you can do is punitive. Or work with things like EPA or a lot of other inspection agencies where their goal is compliance, and trying to figure out how do they efficiently do inspections where you can comply but still make sure that you're being accurate. Some other work we've done around criminal justice, looking at people's historical behavior and trying to figure out, today our criminal justice system has a lot of problems. Most people in our criminal justice system have previous mental health issues, substance abuse disorders, homelessness. And so often our criminal justice systems, our jails and prisons, are really functioning as large healthcare organizations, mostly mental health. So if we can identify people who are at risk of getting stuck in the criminal justice system early, can we redirect them to care that they really need, which might be mental health care, which might be homeless shelters. Now, if you imagine all those issues, all those things I'm talking about, replicability and reproducibility means something very different here. Right? When I write a paper about something like this, I cannot release the data that goes along with it because it's extremely sensitive data. At the same time, I make mistakes. And I want to be able to figure out, how do I check my work? Who validates my work? It can't be a random person on the street who, or even a fellow researcher who doesn't have access to my data. So when we think about sort of reproducibility and replicability, there's sort of 2 or 3 dimensions of that. One dimension is, could somebody, sort of validation, should somebody be able to check and validate the work we do? Yes, they should. How should they do it? That probably involves access, sort of privileged access, not open access, right? And we have some mechanisms of doing that, but not enough. Second is for that, so one of you to sort of say, hey, I wanna validate this. It's not as simple as me handing over my data and my code. You actually have to understand the domain. You have to understand the issues, the problems. You have to invest a lot of time before you can even start looking at my data, looking at my code. Well, you made this decision of linking these things together. And I made certain decisions around record linkage, around imputation, around modeling, around evaluation, around metrics. You can't just say that's a right or wrong decision because you don't have enough context. And criminal justice researchers don't have enough understanding of our field. We don't have enough understanding of their field. So in theory, I could provide you the data, but that doesn't give you anything. You don't have to spend a few months just understanding this domain. How do we do that? What are the incentive models? All that stuff? I don't have any answers. But so that's just one is validating what I've done. Now, replicating means a few different things. So replicating could mean taking the same problem and the same data and replicating it. But in most cases, replicating means if I did some work with Chicago or with Kansas City or with Syracuse or Cincinnati, would it work in a different jurisdiction? Would it work in a different city? for the same problem. That, for me, is replicability. And one of the projects we've been working on is with what's called the Chief Data Officer Network around the country, basically using that network to see, can we replicate something we've done in one city in a different city? Does the process work? Not even the specific models, but just does the process replicate to solve the same problem? Another dimension is, does it replicate and be reproduced to solve similar related problems? So we've kind of come up with different ideas around what it means to what are some templates around doing data science in social good settings, right? Early warning systems, prioritization systems, routing systems. And in those you can say, look, if I've built a solution to solve some sort of an early warning system for police departments, could this work for an early warning system for a school district or a college that's trying to detect which kids might be at risk of dropping out and need extra support in order to graduate? Does that replicate or reproduce? Because some of the parameters are similar, but again, the context is very different. And I think that the challenges that we see in making this happen, some of them are usual challenges, right? It's access to data, access to people who can understand the data. But I think the other problem we see is a lack of people who know how to do this type of work, right? So we spend a lot of time doing training. We've got a program called Data Science for Social Good fellowship program that we run that's really around getting our grad students to really understand these problems, not in a way that most grad schools teach them, which is you give a student a matrix and a metric and they run a for loop, basically what Chris was talking about. Run a for loop in that matrix, a bunch of metrics, and you produce that another matrix, right, which is your results. But how to actually solve the real problem? I've never seen a textbook in machine learning that talks about how to actually evaluate a machine learning system. We use precision recall, AUC, F1. None of those matter in most practical problems. And so I think we really lack an education curriculum that helps people learn how to solve these problems. So I think that's a big gap, is teaching students, but also teaching people in these organizations, because eventually they're the real validator. That if we can educate them internally, not to be experts at machine learning, data science, all the buzzwords, but experts at understanding what does it mean to validate. Because they may not be builders of these systems, but they're clearly the consumers, and they need to be validating these things. So I think it's kind of critical to make sure that we do that. The second thing is, and this was the keynote talk really talked about that today. It was like, we have no clue what ground truth is in most of these problems. Most of our ground truth comes from some sensors that we have deployed. And it's collecting some data, and we assume that it's ground truth, right? So take cities that are looking at 311 data to figure out where to deploy different services. Well, the kind of people who call 311 for certain problems, we know it's all biased, but we can't correct for it again, but we can do something about it. We can augment it with active data collection that samples for things. Take all the hype around predictive policing. We have no clue what crime ground truth is. Nobody knows about crime data. All we know is reported crime, and that's a function of where the police is deployed and people calling in about crime. But we still use, there are tons of papers, hackathons, programs kind of running, building these models and saying we can predict crime. No, you cannot predict crime because we have no clue. And right now I think we're at a point where more and more governments and nonprofits, people solving important problems, are getting to the point where companies were 10 years ago, trying to use data and trying to be more proactive. And I think these problems that we're talking about, we have to help them make sure that they do things the right way, because there's a risk. But we also don't want to discourage them all the time, saying you shouldn't use data, because that's risky, because that's not, that could be bad for people. So I think there's this middle ground we have to play, where we have to be cheerleaders to make them use data, but we also have to be kind of the gatekeepers and caution them. And so I think some of these challenges around replicability, validation, reproducibility are critical for public policy problems that I face. And so I'd love to have a discussion around those and see if we can at least come up with some starting points to tackle those and learn from other fields if people have been doing that more effectively. So thanks.
I'm the final panelist, so we'll move from here into the interactive portion. So I'm sure all of you have questions. I know I have a lot of questions for my fellow panelists. So, please get them ready. This is a really unique collection of people, as is the collection of all of you that are in here. And there's a really important discussion that we're having, we're about to have. So, my name is Dave, and the company that I work for is called datascience.com. My email, I'm going to give you guys a few different ways that you can, a few different things I would love for you to follow up with me on. And the way you can do that most easily is through email. And so it's just dave@datascience.com. So among those are, there's a project I'm going to explain briefly that we're doing that's open source on model interpretability. So there's a certain depth to which no one here can see a model, particularly deep learning models. We would love contributors on that and applications on that. So that's one I'll talk about in a bit more detail. And the other one is you can remember dave@datascience.com and then bigdatahubs.io. Most of you have already been there. If you haven't been there, that's where you can access the resources that part of my job is to deliver to you. So, and I'll tell you a little bit about those resources as well. So first, with these resources, the data science platform is a way that you can run cloud computing and machine learning in a collaborative way. Those are available. My job is to deliver those to people in the academic and government community who can use them, so like all of you. And right now, the best way to use those is through this NSF Big Data Hubs program. Go to bigdatahubs.io if you haven't already. Sign up there. There's some demos on the upper right-hand side, and you can see what's available there. And happy to answer questions about that to anybody anytime here. In terms of model interpretability, there's a real phobia that people, let's say outside of this room, have of even kind of touching data, let's say even from the linear regression standpoint, if they're not particularly familiar with matrix algebra, which most of the world is not. And that phobia can prevent them from A, using it, but then B, it can create a feeling of suspicion, where you're like, I'm suspicious of this data science. So that's one aspect of it that needs to be cured as a society. We have to get beyond that. In the same way, maybe people were suspicious of genetics, which they should be, but nevertheless, everybody is taught that, and we're comfortable with it by and large. The other component is deep learning, which is by definition non-human interpretable. Some of you are more experts than I am in this, but when you get deep into the hidden layers of neural networks, we've actually are now relying more and more and more and more on models that simply aren't human interpretable. So there's ways to mitigate that, and one of the ways that to mitigate that is through designing software that will pull out different features which are human interpretable. And so if you're interested in that element of the standards, there's a project called Skater that we're developing, which is fully open source. We need help. We've built it on a academic government project called Lime. It's written in Python, but again, it's called Skater. So if you look that up on GitHub, then you'll find it, and we could use contributions for that. And finally, I will just say my view on standards generally, which is that the platinum standard, I don't know exactly what's wrong with me that I felt like I had to go a level up here. But my vision of the gold standard is proficiency in data. So similar to what the other panelists were talking about, there is no, regardless of where you're going across domains or within a domain, there's the pace of development of both the volume of the data as well as the context and the computational tools is well beyond any government agency or standard making agency can trace. But what is within their capacity is the ability to give, to train people to be data scientists or to be data science savvy. And so that level of proficiency really needs to be the standard for people to collaborate across domains and within domains. And I'm happy to talk about that for you too. Thank you.
For the panel, in your experience, how does, if you've been able to share your data, how has that worked versus how has it not worked? And if you have examples, that would be excellent.
So one thing that we did was a project with the city of LA using Waze data. And so Waze data that you all generate when you're in a car, your geolocation data, obviously that's private, you hope. So who knows, what you're doing? Well, only you and, of course, Google, right? And so how does that, when that information goes back to cities through certain programs, which I can get into later, it's anonymized, and it's anonymized in a very clean, a standard way. Anonymization of data is a very mature field of computer science, and I would challenge anybody who has data that they feel like, hey, this is too sensitive to share. There are techniques that can be done to anonymize it such that it can never be reverse engineered to the extent that's mandated by the government agency or whatever privacy contracts you've signed with your data sources. So we've done that with LA, and what we're able to do then is provide Waze analytics that anybody else can also use based on driving patterns in LA. So that was one.
Hey, can I sort of? I think you're overpromising a little bit. Right? I don't think there are ways of anonymizing data that keep data still useful under all circumstances and still preserve. I have never seen a data set that hasn't been reverse engineered, if tried. And I think most privacy researchers, including everybody doing differential privacy, pretty much, they won't guarantee anything on the usability side. So I don't think we want to promise our consumers that we have, and I'm it's a discussion, so I'm arguing because somebody has to argue. But I have not, I don't think any of my organizations I work with should be putting their data out in an anonymous way because either the data won't be useful as a way to solve the problems that we care about, or it will be risky. And so unless we have really good ways of doing that, I'm not sure if that's the right approach, but I would love for you to push back and say, no, you're wrong. We have guaranteed ways.
I'll do a quick one and then I'll open up. So just briefly on that, I would actually say take the opposite polar view and feel comfortable doing that. So yes, I can promise that, and we can talk about that later. But one example would be the police data. Police in Chicago contribute to what's called the SWITRS database, SWITRS, and that is a global national database, voluntary, that gives you standardized information about the accidents that have occurred. I can't find out exactly who it was or who the person was, but I can find out a group of standardized information. That's just one example. Volunteer standard, global, cities across the country and states participate in it, and it's available at the national level.
I'll jump in here too, just maybe I shouldn't be too active as a moderator, but this is pretty applicable to our research on the Big Data Hub on digital agriculture. So one of the data sets that we're potentially working with is aerial imagery of farmers' fields. How would you anonymize that when it's literally pictures of their fields? Just as a...
I guess it depends on what you mean by anonymization, right?
Well, yeah.
What attribute are you trying to hide, and what attribute are you trying to expose?
So in this case, the farmers have kind of vested interest in making sure there's not too much data about their particular farm. So I don't think they'd mind having that imagery out there, as long as it was not traceable back to their particular farm. The only problem is it's literally pictures of their farm. They don't want insurance companies to be able to maybe predict crop yields, or state agencies to be able to see if they're maybe not engaging in regulations properly. So in my view, that's maybe one type of data that probably can't be very anonymized, just given the fact that it's literally pictures of what you want to do. You could maybe strip out geographical information, latitudes and longitudes, and might get some more out of it.
But even then, there might be a unique size. This is a unique shape of a farm.
Yeah.
And if you know the shape, that's enough to know who it is.
Or that river.
Right, that's what I mean. I think it depends on what your goal is with that data. The goal is just to look at the general health of the farm on average. You don't even need the image, right? Calculate the health index. Throw everything else away. Now you can average over the entire state the health of the crops, and that's anonymized. but it's not very useful for certain
Exactly.
tasks.
Yeah, I would agree that the key is like the explosion of the, what are you trying to expose? And so if you're trying to expose health, then that's when I say at that level, I maintain that there's a way you can anonymize the data for that. Now, the raw data, I'm not saying you can always expose the raw data. In fact, I would say you should never expose the raw data, and disposing of that data and securing it is a huge challenge. What is much easier is taking the variables that you will expose, that you're interested in, and then bringing those out in some way that they can be shared without violating the privacy of the whatever crop circles are in certain fields.
Hopefully cross circles.
Can I say that in the education area, actually one of the first big releases of a data set was by MIT and Harvard, and they used k-means anonymization to do this, and they actually wiped out most of what many people would call most of the interesting people. And so one of the thoughts, though, but they did provide a really useful data set because even at just the basics, it provided us with a set of ranges of what people could interact with. So people started writing analyses on this and then sending that code to MIT to run. And so what we start to do more and more in the education area is have tiered access. And so if you want very broad access, download it off the web, then it's going to be heavily redacted, maybe even fabricated. And then if you want closer access, then you have to have a certain IRB and a relationship with the university. If you want even closer access, then maybe you have to have a different relationship with the university that allows for more collaboration and so forth. What we're aiming to do now is instead of sharing the data, share the computational infrastructure, and then try and scrub the results of the process. So often in the field that I'm in, people are interested in predicting an outcome that we all share. We're all interested in dropout in these courses. We're all using different techniques to try and predict that, and we just care about different accuracy numbers. And so the actual cleaning or scrubbing of the result is pretty straightforward, and you can layer on top of that IRB protections and data use agreements. So that's kind of the norm in ed data.
In biomedical research, we kind of have the data comes from people, right? So we also have this problem with anonymization. One strategy I've seen that's interesting, a nonprofit that we've worked with has put the choice on the patient or on the person, right? To say, we're gonna anonymize the data the best we can, but if we were to share this, you have to be aware of the fact that you may be traceable, right? I don't know how good their counsel is supporting that, but I think that's one strategy that makes sense. Some people want to share that information if it's gonna help another patient. That makes sense. And then we also have the distinction, so we don't have a social network for medical records, but we do have a social network for MyFitnessPal or Fitbit. People share their wellness data. So it's just, I'm gonna make this more trivial than it is, but it's a matter of gathering that data, scraping that data somehow. The NIH, to your original question about how is data shared, the NIH has done a really good job of creating a repository of omics information, so genomic, transcriptomic, where if you're a NIH-funded researcher and you generate data based on their funding, you have to submit it back to the NIH as a database, and that's all freely available to anyone in the world through their website. And you can embargo it if you're publishing on it and you need to have some time, you can do that as well, but that's been, they have this infrastructure that's very well used in bioinformatics. There's some ethical things around it. If I just go use somebody else's data, should I attribute it to them? Should I make them not? Those sorts of things, but I don't even think so. Those are being addressed right now. So.
Oh, we have a question. Yeah.
So I'm glad to see this conversation and almost sort of polemics come out right away in terms of sort of this open versus closed data, because I think we sort of are on one side or the other very often, where, for example, open data seems to be sort of the answer to everything, or the opposite is closed. And I think this runs sort of right in the face of sort of trying to get more sort of corporate involvement, where obviously the data very often are their intellectual property, and that's not going to happen. So I'd be interested to sort of hear more about what maybe sort of middle ground might be able to be obtained by some of the panelists. I certainly have ideas on that. I think other people do here as well, but ways in which we can democratize, maybe without sort of just making the assumption that everything has to be open.
I can kind of give you two examples of what we've, but I think one is, and neither of those are kind of revolutionary, right? They're obvious what you would think, but they actually work. So one is getting buy-in and trust. If you're going to somebody and say, hey, I need your data, the first reaction an organization has when an academic goes to them is, okay, you want to publish something that we don't care about, or if it's government going, it's you want to expose something we're doing, right? Once they understand that you actually want to help them and solve their problem, which requires a lot of invested time into understanding their problem and helping them and giving them something back, they're coming to you all the time. I mean, I have a line of government agencies who want to work with us, I just don't have capacity. So what I recommend to people who want to do this is you can go build that trust, or you can use an organization like me to come through me and say, hey, if I trust you, I can transfer that trust over and say, no, this person really cares about solving your problem. So that's one tactic, is finding a trusted organization. That's not going to be public data. You still have to sign legal agreements and be on an infrastructure that's secure. You can't have any grad student have access to it on their laptops. All of that being said, if you really care about solving the problem with this type of data, it's not that hard, but it does require some commitment and some investment of time and effort. The second model is these sort of data enclaves at different levels of security, right? So one of the programs we're running right now is a training program jointly with NYU and the University of Maryland that we're training government agencies in using machine learning and all the other things. And the infrastructure we've created is we've gotten very confidential individual level data from Department of Corrections in Illinois, Department of Employment Security, where every individual, every quarter when they get paid amount of money, Human Services, every individual, linked all those things together. And now we're using this as a training data set. But the pitch to these government agencies is, hey, all these people, when we train them in this environment, they're producing tools and products that are on your data. And you can now use, it's secure, it's safe, it's FedRAMP compliant, it's expensive, but all that, they don't have to put in their own effort, and they're just putting in the data. And our training is producing things that they can now use. So I think and there are lots of examples of that around the country where some enclaves are really closed, some of them are sort of semi-open, where you sign an agreement, confidentiality, and you might not have internet from inside and all these different constraints that we all hate. But they are effective at getting data out of these organizations and making it available to researchers and practitioners who care about solving the problem.
So I think it can really depend on the domain. So in higher ed, where I'm at, and actually I would say 80% of this room is probably faculty or students in higher ed, we're actually very rapidly losing control of the data to vendors. And so especially with cloud computing, when it was on-prem computing, it was kind of, you had the server there, it was your data. But when it's cloud-based, there's a lot more resistance to sharing that data, and technically it's a lot harder too, because there's often one big data store that has all of the institution's data in it, not just a single class or a single institution. And so it's actually quite worrisome because as a higher ed, I guess in higher ed we're losing some of the business intelligence we could have access to. And so one way to deal with this is through procurement contracts, specifically looking at data sovereignty and considering it a strategic asset of the institution. But I wanted to share also an anecdote. I was talking with a senior established researcher at a private university who was doing a lot of data analysis, and they were working with some leading ed theory folks in the field, and they were trying to replicate some of this core work that a lot of ed theory is based on, a lot of practice is based on right now, and they were unable to replicate it. But they weren't going to publish that. So that was actually seen as quite a failure, that they couldn't replicate it. Instead, they were going to keep tweaking various parameters and keep trying again and again. And so most of the people in this room will realize that's really dangerous. We should be publishing null results, especially in something like education where it's heavily still theory-driven and not data-driven. And I think that that's another another challenge that I've run into when working with different ed vendors. They're happy to publish the success story. They're not as happy to publish that they wasted a bunch of time talking to us and didn't find anything because their data was crap. And at the same time, we're driven to publish. And so that's one of the challenges anyway in the ed domain.
Kate or David? No? Okay, so if we don't, I kind of have a follow-on for this. So in the machine learning community, or at least in computer vision and neural networks, and even in evolutionary algorithms, both of which are more kind of my background, I think a lot of the reason we see big data or deep learning as popular as it is now is that there's been data sets that have been published which are good benchmarks. So you have the handwritten digits database, you have Cypher, tiny images, all these things, which make nice problems for algorithms researchers to compete against and publish on with a set, kind of like benchmark data sets to compare against. In your particular areas or fields, are those things being discussed? Is there movement towards making, here's benchmark data. It might not necessarily be real, but it's something that we know and we can have people compare against. That gives a way to actually compare different research results and things along those lines.
So one of the things in the transportation domain that I can comment on is just a few examples. I mean, one would be there's some studies, distracted driving is one of the major interesting questions in terms of health and mortality in driving. And in order to find out if someone's driving distractedly, it seems like there's a number of studies that have been done which are focused on sort of creating toy data and data from people who are in a specific environment, subjects through the IRB. And then of course there's also the data that everybody here is generating through your cell phones, with your cameras pointed at you as you're driving. And so in that domain, I can say that there is a lot of interest at the federal level in creating exactly that kind of a data set that's a clean layer that everybody can agree upon, everybody can access, everybody can use. Whether it's going to be just the laboratory data from these 200 subjects, or somehow combined with the greater pool of available data that corporations have. But they're actively trying to figure that out. I think precisely to create that type of a model. Yeah.
So in the bioinformatics area, the biggest, I think, application that I've seen of machine learning is in pattern finding. So it's, approaches that are being applied to DNA sequence data. So for example, the human genome is 6.1 billion characters long, and identifying very short but unique patterns within that DNA sequence, that's been really the biggest area that I've seen machine learning in. And we do have a pretty good understanding of what patterns are there, where they're located. That I think that's the best example. Everything else is still kind of up in the air. It's all a question. We don't know. We know everything, but we don't know anything. So I think that there's really there's still a lot of low-hanging fruit in the area of machine learning in bioinformatics and biomedicine that's still there.
So kind of as a follow-up to that, to my question, say in bioinformatics in your particular subfield, for the algorithms that people are using, are there data sets out there that are sort of benchmarks? A lot of the work I see in that area is, okay, we use this particular algorithm to find, say, we were looking for transcription factor binding sites or something like that, and they run it on their data set, and here's what we got. But I don't know if this algorithm compares to this other algorithm, if it really even works. I mean, it seems to. The results make sense biologically, but is it doing everything it's supposed to?
Yeah, my short answer is no. I don't think that there's a lot of, even in NCBI, the resource that I mentioned, one of the problems is that the data is still kind of siloed. So you can't compare data from different, they're generated using the same tool. So we have Illumina platforms. You can't compare the same data generally because they use different mice, or they use different sample numbers or different effects. So it's like very small data silos as well. So it's very hard to generate benchmarks. And I think a lot of people, that overwhelms them, so they avoid it, right? And they do a proof of concept, but they don't take it the next step. in my opinion.
People do create data sets that are benchmark data sets, but it's still pretty early days and it's only for some applications.
I think one question we want to ask as a community is, do those standard data sets, are they more helpful than they hurt the community, right? So we've seen the UCI data sets being amazing at generating a lot of random new methods that may or may not be useful, but everything we do overfits to UCI data sets, and I can't believe people still use data sets that were generated in the 80s. So I don't know if standard data sets are a good thing or a bad thing. You know, the Netflix data set being put out there resulted in non-negative matrix factorization being a thing that was scalable and worked. Now, how many applications is it actually being used for in practice? Probably nothing. So I think it does result in new research and new methods. And what we don't know is how applicable those new methods are to real problems. And how do we define that delta? How do we define the delta in real problems, real data, real problems versus public data, public problems? And even the dimensions, like right now we don't do machine learning as in, well, if your data is of this type, you should use this method, because we don't even know how to characterize, you know, we can do a bunch of different metrics, but we don't really know how to do that. Which is also a problem with, you know, last night I was talking to Carl about competitions. We have a bunch of competitions. They're mostly useless in teaching people anything, or even creating new research, because half of them have column names as column 1, column 2, column 3. So we're basically teaching people how to take a matrix and run a for loop. How do we make that, you know, how do we define the delta between public data and real data? And can we characterize a problem as, this delta is small, so you should use this data set. This delta is really large, so you probably don't want to pay attention. I have no idea, just, but if people have thoughts.
So I just want to push back a little bit on the competitions front, because competitions do a lot of other good things. They can really energize and give students a focus to start thinking about how they would use this different techniques. I think they can create an in a moment comparison as well, like in this year with this data set, you know, with this competition, what were the interesting techniques that came out of it?
Who cares about the techniques? I mean, we're trying to solve a problem. If that technique doesn't solve this problem, it gives students the fake satisfaction of thinking they can actually solve that problem. It isolates them from understanding the domain, because most competitions don't come up with a human being who can explain the domain to them. It stops them from doing the most important thing, which is problem formulation, feature engineering, because they don't know what these features are. That's column 1, column 2, column 3.
Well, so actually, that's my biggest hit against competitions, is that different people, so we have hyperparameter selection, we have feature engineering, we have model selection. All of these different things conflate together to give you your how predictive it is. And often you can't tear apart which one did what. And I think that that's a big problem with competitions. But I do think that there's value in comparison. Like, I guess the competition is not just necessarily about solving the problem, because all of the methods solve the problem. It's to what degree do they solve the problem, and how can you compare them? And I think that that's where, that's one of the benefits they have. But I don't think they're the...
No, I mean, honestly, I think the model of competitions is wonderful, right? I think if we did the competitions with a specific focus, say, look, the goal here is to do exactly what you said. We bring in experts from that domain. We actually give access to the right data. We collaboratively build these solutions, compare them. That's a wonderful, I'm not against competitions. I think what I'm arguing for is competitions the way they are done today, majority of the time, don't achieve those things. I mean, I get all these emails from people about, hey, you know, I think I'm really good at machine learning and you should hire me because I came 3rd in this Kaggle competition and 9th in this one and 12th in this one. And I can't tell what this person knows with those, because they think they know everything, because they can beat Kaggle competitors, and I don't know what that means.
I think there was a...
What do you guys think? I mean, what have you found with sort of these competitions?
Well, I think based on the, can you guys hear me okay in the back? Yeah, okay. So I think that the question of the benchmark data sets And if you think about a competition, by definition, you're talking about a benchmark data set, so they're kind of the same question. The way that I would look at it is if you look at the computer vision benchmark data sets, which are among the most mature, and you look at then the progress of deep learning across both academia and the private industry and the collaboration there, then you say, hey, there's a model that has surpassed anybody's expectations. So as a government or as a citizen, what do I want from my government? As a government, what do I want to provide to my peeps? And in each sector, you should provide, the government should be providing, or the NSF, that kind of benchmark data set. Will it be flawed? Yes. Will it be, there'll be issues with it, but that's really the job of an overarching, it's something that the government can do, all of you can do, is to create that benchmark in the domains. Obviously, there's the genomics benchmarks that are out there, and where there isn't a benchmark, then I think there should be an organization creating it. With all its flaws, to model on that, the success of, for example, computer vision.
Kate, do you have anything to add? Okay, so I guess we have questions from the audience.
Sorry. Yeah, I'm Dan Reed from the University of Iowa. What we've done here is do what we all do as geeks. We've lapsed into a technical discussion. So I want to elevate it back to a social issue. Which is reproducibility in science is as much a social dynamic question as it is a technical one. And there's a lot of bad science done now, I would argue, with big data, frankly, because it's easy to do. I mean, it's easy to do the thing that produces the paper. And it's coupled with, for those of us who are academics, this publish or perish pressure that has escalated. And so here's my social question. How do we actually limit publication to good science, given the ease with which people can do these experiments? Because in the past, if you had to construct unique scientific infrastructure in order to conduct an experiment, there was some rate-limiting process on it because it was actually hard to get to the point to get data to ask a question in the traditional experimental approach. So talk, if you would, a little bit about that social challenge that we face, because we risk losing credibility. And I think if we do, and I'll stop pontificating after I say this, if we lose scientific credibility in the eyes of the public and the funding agencies, our research will disappear.
So my short answer is I don't have a good idea other than starting as individuals in the classroom, promoting peer review, promoting good peer review, and if you don't know, if you're not an expertise in that field, don't peer review it. I think that's starting at the individual level, but on a larger scale, I don't know how to do better. I know preprints are becoming a bigger thing now in biomedical research, where you can get comments from the public and get, maybe then you can, they'll tear you down if you're doing bad science or lift you up if you aren't. But I truly haven't seen any very innovative solutions to this problem in biomedical research.
And I would say in the PLOS era, that it's open. You can't put PLOS back in the PLOS box. So what we need to do is educate just people and citizens, at the individual level, and then the government will catch up to that. And the good news is that that's actually not becoming easier and easier and easier. All kinds of programs like you're all been talking about, Data Science for Social Good. Everybody here is working on how do we educate people quickly, in a few weeks, in a few months, at the high school level, so that they can make their own accurate judgments. And I think things have to go that way. That credibility has to be, we have to deliver that to, both the government, but also people too.
So one of the things that I've seen in my domain in the last 15 years change is the breadth of techniques that are now brought in. And one of the problems at any learning analytics or ed data mining conference is finding somebody who can review the article, because people are pulling econometric techniques in, advanced statistics techniques in, kind of computer science sided machine learning techniques in, and using a blinding array of output measures, usually whichever one was the best, as the thing that they're reporting on. And I don't know what the answer is to solve that, but it's had several people have noticed the impact it's had on the quality of accepted articles, because even though they might be technically competent, they're rather uninteresting. And so one of the challenges with that, though, is we want to allow for incremental research as well, and we want our students to be able to pick up different techniques and use them. But in an interdis field, we're being swamped by this issue that we can't find qualified reviewers.
Perhaps think about the tenure process. I think that's something a lot of us in this room can control, because it's that loop.
So I wanted to reflect on something Raid said about the challenge of replicability. And Chris, you brought up that table with the Weka results where something is going to be the best, but it doesn't mean very much. So from all the panelists, what do you think is the role of the understandability of our models and to be able to reason with our models, to being able to use these systems in a reproducible way or to even compose them at some point?
Yeah, I think to the previous point and then to that one as well, I think that it's the responsibility, if you're putting something out there, it's your responsibility to make sure that it's human interpretable, to make sure that any algorithm that you used, if you're using k-means, then you have to be able to understand k-means, and we can all hold each other accountable for this, and we can all make sure our students are held accountable for that. You're not allowed to use anything unless you can explain it, and it's a challenge to explain it. And people should be forced to, and we should all be, meet that standard originally. That's I'll leave it at that. That's one sort of bottom-up way.
So I was really glad that Dave talked about interpretability, because I think for the kinds of work I'm doing, there are three reasons why we want that understanding. One reason is our models are wrong a lot of the time, and we want to be able to debug them as developers of those systems, because if we don't understand them, we're going to pass them off to people. If we don't understand them, we can't debug them. The second is a lot of the things we're doing, it's not unlike sort of the advertising world where there are a lot of micro decisions being made, every microsecond. In the policy in the human world, these are decisions that are being recommended to a human being who then has to trust it in order to take an action. And if they can't trust it, it doesn't really matter. So whether they understand math or not, we have to explain to them in their language. And if they don't understand or trust it, they won't do anything about it, which means we'll have zero impact. So the whole trade-off thing works here is, a worse model that's acted on is still better than a much better model that has no impact. I think the third part, which is a little bit more nuanced, is often the types of problems we work on, we don't have the final answer. So what we do is we say, this person is at risk of doing something bad. I can't really tell you exactly what you can do about it, because you as a human being should spend time you understand this person, you understand the domain, but I can tell you this person is at risk, which is very much the kind of problems you're talking about, Chris, is, this kid is at risk of not finishing. The algorithm might not be today, with the data we have, recommend an intervention. So we're relying on this expert in the middle to understand why this person was predicted as high risk, and then with the number of interventions available to them, assign one or more. If they can't understand the reason, they can't assign intervention. If they can't assign intervention, that prediction is just something we watch happen, and we can't modify that behavior. So there's a really critical need beyond just understanding and responsibility. It's in order for impact to happen and things to improve, we have to go beyond just the prediction piece and just the modeling piece, but not just interpretation at a model level, but at each individual prediction, whatever we're doing, identification level, because without that, no action can really happen in at least the problems we're looking at. There are a lot of problems out there in social networking and advertising where, each micro decision doesn't need to be explained. You can understand the bigger thing and the risks are low, but the kind of things we're looking at, the risks are so high that you have to be able to understand them.
So in the ed domain, theory is king still, and it's only lately that sort of fourth paradigm data-driven methods have been challenged a little bit. And the interpretability of a model, being able to probe a model and find out for whom it's working, I think is really important. There was a good paper at KDD last year, the year before, that really focused on this. This Skater toolkit looks great. But it's actually, even in some of the applied communities like mine, it's some base competencies and good workflow. So knowing that you're not training and testing on the whole set, and tenfold is kind of, that was fine in the early 2000s, but now you need a holdout set, and the holdout set can't be random. It's got to be actually something that you would predict on, like the most recent data and so forth. So I think one thing that those of us in applied machine learning areas or applied data science areas can do is start trying to enforce some rigor like this in our communities. But it would be really helpful to have a layperson article written by strong machine learning folks that kind of outlines some of these key points. Because when you're in the community, there's kind of a lot of, well, I'm not sure, do we really need that, and so forth. But if we could come to some general consensus on some of the key issues and the key ways a scientific community could evaluate and protect against those, I think that would actually be quite popular, not just in ed communities, but in lots of computational social science communities.
I'm going to jump in here a little bit just from the computer science angle. I actually think this is something that the machine learning community will probably, it's starting to address, and it'll probably address more. When you train a deep neural network, you use an evolutionary algorithm. These algorithms are stochastic, they're pretty heuristic based now, and you really don't know how it's getting to the answer that it's getting. That being said, I think there's a huge opportunity for these fields to take, okay, I have something that works, how do I reverse engineer out of that something that a human can understand? So I think, and it's my hope, that these communities will actually are starting to see this as a problem, because these tools do need to be understandable. If you're using a deep learning technique in a self-driving car, and you need to protect yourself in the court of law, just saying, well, I trained it and it worked really well on the generalizability and test data, so yeah, that's not going to work. So it has to be taken back.
I think the other thing that you mentioned is really interesting is, the deep learning thing. So I think there are two types of problems we use machine learning to solve today, high level. Things that humans can do but can't scale. Right, so that's all. Most of the deep learning work is we can tag images, we can read text, but we can't scale. So when you do interpretability there, it's just verifying what the human already knows and say, I label this, the Lime work, right? I label this picture as a dog because here's the face, and like, okay, I get it. The second type of problems are the kind of these prediction tasks about who's at risk. And humans are not good at it today. That's why we're trying to use computers, right? So when a system like Lime that you're talking about, and we've been testing a lot of those methods, when you apply those, it says these three features are important. But then the next question is why? So now you need a meta interpretation algorithm that explains to you the explanation that's given by the previous one, because it's at a level of features, and the human doesn't, like, if I knew these features were important, and so we have a really hard time, it's sort of, we keep building layers and layers and layers, but most of the methods out there for interpretation are really focused on the part where humans know how things work and can scale it using machine learning, but we're very much don't know how to deal with things where humans don't know. So then you have to dig deeper and explain it in a much more, almost an interactive manner, where you're almost doing, the information retrieval question answering world, where, why did you predict it this way? Well, here are the reasons. Yeah, but that data source was not reliable. Like, oh, okay, if that was not reliable, here, I'm gonna change my priors, and now it's a new prediction. So you're almost questioning the model as opposed to a one-shot explanation.
This goes back to the notion of interpretation. Even if you go beyond, deep learning, go back to principal components. And even principal components to interpret each component is not easy. That seems to be the crux of the problem. And one more thing about deep learning is that I feel you're passing the onus back to statistics, sampling. It's like if you can train your deep network, can be really shallow, But if you train this this shallow deep network, you can get good results. But instead of using 10,000 images, you can use 3 million images. You'll do okay. So I mean, I feel like this trust on this panacea I think is misplaced. It's really goes back to I know I'm arguing with you, not not asking a question. So I think it really goes back to the stratification of the space, of the parameter space. So I think it's deeper than just running the algorithm. Just my 2 cents.
Yeah, I mean, I think that what's exciting about that, and I think PCA. I think this didn't happen with deep learning. Obviously, this has been around forever. PCA being probably the previous sort of big poster child for non-interpretability often. But what's so exciting is that the 2 angles to approach this are in the computer science. Is a computer science problem, so solving it with Lime and Skater, and that's what we're trying to do, and the resources to do that are great, and everybody does understand the need, so that's very exciting, optimistically. And then the other one is policy too, like this person-to-person trust and policy education. It's just like, how can we as humans trust each other regardless of what our differences in education and background was, and that's really a policy issue, but it's groups like this that make me feel optimistic about that too.
So you all kind of commented on this, that a lot of times we don't know the ground truth. And for example, we're working on transportation data, in particular with Waze. So people report something out there. We know some things that happened and are recorded by law enforcement or DOT. We know those as labels, but obviously we don't have anything, like everything. And then, so we're trying to model the reliability of a Waze report in the middle of nowhere in Iowa. So how do I go after that? How do I?
I mean, with Waze, the feeds have a built-in sort of score for reliability, and so it's just a question of how much data you have, just like any other probability or sampling issue. So the more people that say, yeah, that's a pothole, I just went over the pothole, then the reliability of that score goes up. And so if you're in some place where there's only one person with Waze in the city, then it's the same problem as if you have a low end with any experiment.
But I think you're asking a different question. Is condition on Waze, there's a distribution of people who use Waze. And that the type of roads they travel on is very different than if you were uniformly sampling people, which is the problem with any data source, that there is some distribution that's different from the actual one. So when we do this type of work, we need to invest, not everybody should do it, but some portfolio of the investment should go towards baselining and ground truthing. So whenever you use Waze data, somebody should spend the time and money to also actively sample to make sure you have a uniform sample. That means paying people to look at the street, maybe trying to send cars and collect data. Because without that, you have no clue that your work is actually doing anything. I'm not saying everybody should do it, but I think you should have some portfolio, some percentage of the investment being, let's baseline it, because we could be doing things that are completely different than especially if you're implementing policy that needs to be equitable, right? So if everything is around potholes where Waze drivers go, you're going to fix potholes in white, rich areas, which has happened before. So we don't want to just assume the ground truth is what the sensor gives us without looking at that.
Another quick plug for bigdatahubs.io, because the transportation challenge, because transportation is the perfect petri dish for this, because there's Waze, but there's been sensors that are in the ground, reach sensors, and there's satellite imagery, and there's actually usually people there like clicking, engineers from the city who are like clicking away at counting cars. So there's a really rich wealth of data science that's like serving that purpose, but it needs help to sort of figure out how do we relate these.
I think one other thing to keep in mind is that your population can change over time, as can the quality of the sensors, especially when humans are involved. So Waze in the first 30 days after it launched versus Waze in the last 30 days here might have very different drivers using the tool. It's normed into the positions very well. In the ed data online, we find this too. The population that was coming to free courses 5 years ago when the phenomena really started, very different than the population that's coming now. And so if we build all our predictive models just for that population, it has poor, it looks good on paper, but it has poor replicability.
All right, unfortunately, Melissa told me that I had to be done at 3:15 sharp, and I think that's it right now. Please, everybody, thank the panel. This was awesome. This was one of the more fun panels. And thank you to the audience, too, for a lot of back and forth. That was great.